In this lecture, we'll continue our discussion of probability rules. In particular, we're going to look at something called the law of addition. Over the next few slides, we'll look at a lot of equations, but the point of this lecture is not for you to memorize the equations or the formulas. The point is for you to understand intuitively why the formulas work and to be able to identify in particular situations which formula to apply and how to apply it properly. So the focus is on using the formulas to solve problems and not on memorizing the formulas. The first formula we're going to take a look at is the law of addition. And the law of addition just says if we want to know the probability that either A or B occurs, so event A could occur or event B could occur, what's the probability that one or the other of those two events occur? Then we compute that probability by computing the probability that A occurs plus the probability that B occurs minus the probability that both of them occur. And you may ask, well, why do we have to subtract that last part off if we're talking about A or B or both? But if you think about it, when we're computing these probabilities, right, if we have two events A and B, and we want to know what's the probability that either A or B occurs, well, that's the probability that A occurs plus the probability that B occurs, right? But if we add those two things up, what happens to this part in the middle? We count that part twice, and so we don't want to double count that overlap, which is why we have to subtract that part off in this formula. If two events A and B are mutually exclusive, then we can simplify this formula, right? So remember, the definition of mutually exclusive just says that A and B have no outcomes in common. So this would represent two mutually exclusive events, A and B. If A and B have no outcomes in common, then the probability of A intersected with B, the probability of both A and B occurring, is equal to 0. And if we replace the probability of A intersected with B with 0, then we just end up with this simplified formula that says the probability of A union with B is just the probability of A, right? We take all of this material, plus the probability of B, and we're good to go because we don't have that overlap. So we have two different versions of the law of probability. One when we have events that are not mutually exclusive, and we can simplify that rule whenever we know that we do have mutually exclusive events. So let's take a look at a couple of examples. In this particular example, we'll look at some U.S. Census data, and we'll define a household as being prosperous if its income exceeds $75,000. We'll say that the household is educated if the head of household has actually completed college. Now, based on information from the Census Bureau, the probability that a household is prosperous is 12.5%, 0.125. The probability that a household is educated is 23.7%, and the probability that a household is both prosperous and educated is 7.7%. And so our question becomes, if a U.S. household is selected at random, what is the probability that the household selected is either prosperous or educated? And when you see in a probability problem the phrase prosperous or educated, right, this is kind of the key here, prosperous or educated. That or indicates that you want to know whether the household is prosperous or educated, and implied is or both, right? So or is the keyword that would let you know we're talking about a union sort of probability. So here's what we know. The way I typically start a probability problem is to write down what we know from the problem and write it down in probability form. So the probability of being prosperous is 0.125, the probability of being educated is 0.237, and the probability of being both prosperous and educated is 0.077. And so the question is, if we select a household at random, what's the probability that the household is either prosperous, right, and I'll use a little shorthand here, or educated, right? So we said that's going to be a union, so prosperous or educated. The first question to ask is, are these two events mutually exclusive? They would be mutually exclusive if the probability of both occurring at the same time is equal to 0, but we said that the probability of being prosperous and educated is equal to 0.077, which is not equal to 0. So these events are not mutually exclusive. So therefore, the probability of being prosperous or educated is the probability of being prosperous plus the probability of being educated minus the probability of being prosperous and educated. right? Again, I'm going to use a little shorthand here. And so now we know all of those probabilities. This is equal to 0.125 plus 0.237 minus 0.077. And if we do all of that math, our probability is 0.285. So that's the basic idea behind one of these probability problems. Identify the information that you know, identify the probability rule that you want to use, check any conditions like mutual exclusivity, and then plug the numbers in, and you have the answer. So the hard part here is not the math. The part that's important, or the part that requires some thought, is reading the problem, pulling the right information from the problem, and applying the rule in the proper way. So let's take a look at another example just to make sure that we kind of have the hang of this. In this example, a survey was administered to Clarkson University students asking them about their overall experience, and they were required to select one of three options, or they could choose not to respond. So it was possible for this particular survey that they could leave that response blank. They were not allowed to select more than one of these options. They could only choose one. And the results showed that 4% of the respondents chose not to respond, 26% said their experience fell short of expectations, and 65% said that their experience met their expectations. So if we were to randomly choose an alumni, what is the probability that that particular person would say that her experience surpassed expectations? Again, the way that we're going to approach this problem is to write down what we know and then think about what's left. So in this first part of the problem, if we choose an alumni at random, what's the probability that she would say her experience surpassed expectations? We have several pieces of information. We know that 4% did not respond. The probability that they said fell short was 26%. The probability that they met expectations was 65%. And this question wants to know what's the probability that her experience surpassed expectations. Well, we can go back to first principles here, and we can use the law of complements. We have four possible responses. Those are the only four responses, and so we know that because we have probabilities here, those the values of the outcomes in our probability space have to add to 1. So if we were to add all of these probabilities up, they would add up to 1. And we could think about dividing the probability space up this way, right? We have all of these different options that were anything but surpassed expectations, and then we have surpassed, right? So we kind of have not surpassed versus surpassed. The probability of not surpassing our expectations would just be the sum of the probabilities that we have up here. So the probability of not surpassing expectations would be 0.04 plus 0.26 plus 0.65. And if we do all of that math, we could add those values up, right? And that would give us 0.95. And the probability of surpassing expectations, we can use the law of complements, right? And the law of complements just said the probability that an event happens, probability of surpassing expectations, is just 1 minus the probability that the event does not happen. So 1 minus the probability that they did not surpass expectations, right? We just computed that. That probability is 0.95, so this is 1 minus 0.95. And so our probability in this case is just 5%. So the probability of surpassing expectations is 0.05. Okay, so we haven't even applied the law of addition here. Well, we have actually, because we use the law of addition in adding up the probability of no response plus the probability of fell short plus the probability of met. And we were able to add those probabilities up because these are mutually exclusive outcomes. How do we know they're mutually exclusive outcomes? Well, we know that they are mutually exclusive outcomes because the students are only allowed to select one of these outcomes at a time. So they're not allowed, for example, to select fell short and met. So the probability that they could select fell short and met expectations is just 0. There's no overlap between these responses. So in this particular situation, all of the responses that we have here are mutually exclusive responses. So carrying all of this information forward, there was a second question associated with this problem. The second question said, what is the probability that the alumnus would say that his experience met or surpassed expectations. So the question here is, what is the probability of meeting or surpassing expectations? Okay, so in this case, again, we need to recognize that all of these responses are mutually exclusive because the survey was designed in such a way that the students could only select one of the responses. Because they're mutually exclusive, we can apply the law of addition. This is a union question, either met or surpassed. So we can apply the law of addition, and we can apply the version of the law of addition for mutual exclusivity. So this is just the probability that they said met expectations plus the probability that they said surpassed expectations, right? The overlap, the probability of saying both met and surpassed, is just 0, so we can apply that mutual exclusive condition here, and we can just do the addition. So if we do the addition here, that's 0.65 plus 0.05. We computed that from the previous problem, and that just gives us 0.7. So that's how we begin to pull these probability problems apart and apply the different rules and understanding that we have about probability. Probabilities sum to 1. If we look at the entire list of values from the sample space, we use the law of complements, we use the law of addition, and we also took advantage of the fact that we understood what it meant to be mutually exclusive. The next step in this process is to understand how to compute the probability of an intersection, the probability that this event occurs and another event occurs at the same time. So in the next lecture, we'll continue with our probability rules and talk about the probability of an intersection as well as the concept of independence.